This is the presentation for Team 7, also known as the Power of Dawn. I am Matt, and I will be joined by Kara, TQ, Zane, and Jenny to discuss a cumene production facility. Over the last 12 weeks, our group designed, modeled, and analyzed the feasibility of a 591 million pound per year cumene production facility. This facility utilizes the Nitlion Chemicals new catalyst that catalyzes the reaction of propylene and benzene into cumene. This new plant will be located in the U.S. Gulf Coast. After modeling and designing the plant, we spent time to evaluate the economics of this process and found that it projects to create $248 million per year of revenue. However, after the lifetime of the plant, we found that the net present worth projects to be negative $8.3 million, meaning that we were not making money. However, with a few small tweaks, we found that we were able to make money using some alternate process studies. This presentation will begin by talking about the product and the specifications. We will then talk about our overall process and the block flow diagram. We will then discuss the economics and then finally talk about recommendations based off of our findings. So starting with going over some of the specifications that need to be met in order to have a functioning facility that operates safely and produces a sellable product. Looking at our capacity first, you can see the capacity converted to pounds per hour on the screen, and we were able to achieve that within 0.01%. Next, looking at the product itself, making sure that it meets all of the requirements to be sellable, and it does. Looking at all of our reactors and their conditions, making sure that the temperatures shown here, as well as the pressure drops and the inlet conditions, are suitable for all the reactions and those meet specifications. And finally, for the process itself, making sure that it remains at a safe operating temperature and pressure to prevent equipment fouling was also satisfied. Moving on to some other specs that were not needed to make the facility run, but were recommended to begin the project. First off, looking at the utilization of benzene and propylene in the reactors, converting it to cumene, which we were unable to meet this spec. And then related to that, our fresh benzene, the amount that was going to our fuel or waste, was also over the recommended limit. The reason for this is because of some unforeseen changes to our initial predictions for the reaction kinetics. The main culprit in this is the cyclohexane. That side reaction's reaction constant was about 3 orders of magnitude higher than initially predicted once we fitted rate laws to the supplied lab data. And as you can see from this graph, the cyclohexane is actually peaking before the cumene is, which because cyclohexane is so difficult to remove from benzene, increasing the benzene recycle would actually make our process so large because of the cyclohexane building up that our process would become no longer economically viable. So this is why we were unable to meet those recommended specs, but we were able to meet all of the specs to have our plant operate safely and produce a sellable product.
A BFD of the process used to achieve the required specifications is shown here. I'm now going to zoom in to show you a better idea of how this all works. So benzene is fed from the OBL located 1 mile away. This is sent to a benzene toluene separator, which separates toluene out before most of it ever enters the process. This is done to help achieve multiple specifications within the plant. This purified benzene feed is then mixed with propylene feed in the benzene recycle and sent to the alkylation reactor to form cumene and other side reactions. This purified benzene stream also mixes with a benzene recycle and DIPB, which is formed in the alkylation reactor to be sent to the transalkylation reactor. These 2 reactor effluents are then mixed and then sent to a single distillation column. This benzene cumene separator then splits benzene out the top and cumene out the bottom. The benzene out the top is sent to the benzene propane separator, where it is separated into a propane-rich stream and the benzene recycle. Out the bottom of the benzene cumene separator, cumene is the lightest component. So this is then sent to a DIPB cumene separator where cumene product exits the top of the distillation column and DIPB and other heavy components exit the bottom. This is sent to a final distillation column where heavies are removed from the system and out the bottom of the distillation column, and DIPB is sent out of the top of the distillation column and recycled back to the transalkylation reactor. Both recycle streams have purges to prevent buildup of inerts within the system. After determining all the major components of the system, everything was sized to determine a capital cost for the plant. As seen here, the alkylation reactor shown in the green pie slice is one of the largest portions of the plant capital. This is due to the shell and tube design and the fact the two of them have to be bought for the process to operate smoothly. This $7.3 million cost does not even include the $4 million required in catalyst put into this reactor. The benzene toluene column is also another large cost, and it is a large cost because it is a large distillation column due to high reflux ratios and boil-up rates. Another large cost is the benzene cumene column, since it is the first distillation column after the reactor effluents are combined, so it has very large flows through it. The final large distillation column is the DIPB cumene column, so it was expected to have a decent portion of the capital cost. After estimating the IBL capital cost, the OBL capital cost was then estimated using previous bids. This OBL capital cost was found to be approximately $14.7 million. Out of this $14.7 million, over half of it is required to upgrade the utilities of the plant. This is a necessity since there will be a larger demand for steam, power, and other various utilities within the plant due to the cumene plant being added to the overall plant. After this was determined, the overall capital cost could be determined. This includes the IBL, OBL, escalation since the process takes 3 years to complete, and project contingency. Project contingency accounts for any hiccups in the process that may occur during the length of the construction period. Other costs include pre-operation costs and startup, the catalyst for both reactors, which was not taken into account in the IBL capital cost, and a home office. After determining these capital costs, the operating costs could then be determined.
The total operating cost for the plant was determined to be $231 million per year, with the cost breakdown shown in cents per pound of cumene product in the pie chart. The majority of the operating costs are due to the purchase of raw materials shown in blue. Almost 100% of the raw material cost is due to the purchase of the benzene and propylene feeds, and comparatively, the cost of purchasing the reactor catalyst contributes very little. The waste cost is the next largest contributor to the operating cost. This cost is combined with fuel to determine the byproduct cost, so fuel credits gained from plant operation will offset this large waste cost. This reduces the total byproduct cost by 0.37 cents per pound of cumene product. The remaining costs of selling, general, and administrative fees, utilities, taxes, and labor contribute a small fraction of the overall operating costs, so any variations in these costs will likely have a negligible effect overall. This figure shows the cumulative cash flow in blue and the NPV12 in orange of the company over the plant lifespan of 19 years. The NPV12 refers to the net present wealth of the company with a 12% discount rate. Looking at the figure, there is a sharp decrease in both the cumulative cash flow and the net present worth in the first 3 years. This is because the plant does not become operational until year 3. So no profit is being made in this time period, and all of the capital spending is made here in order to build the plant. Even though the cumulative cash flow becomes positive after 7 years, meaning the plant is making more money than it spends, the profit made is not enough to make the net present worth positive over the lifespan of the plant. The final net worth of the company after 19 years is negative $8 million, which means the current design is unprofitable. Therefore, under the current conditions, it is not recommended that the plant be built. The ATROR refers to the rate of return, which measures how efficiently capital resources are being utilized. If the rate of return is at or above the hurdle rate of 15%, it indicates that the investment is likely to be profitable. Under current conditions, and with a sale price of cumene of 42 cents per pound, the rate of return for the plant is 8.7%. If the sale price of cumene were to increase by 0.7 cents per pound, the target 15% rate of return would be reached. Under these conditions, the plant would be profitable with a net present worth of $10 million, and the plant would be recommended to be built.
So from our sensitivity study, there are two factors that had the biggest impact on the rate of return of our project. So the first factor is the raw material cost. So this analysis will show that the higher the raw material margin, the better rate of return. And as you can see right here, this chart shows the historical price of the benzene and the propylene and the total raw material cost to produce 1 bar of cumene from the year of 2013 to 2020. This graph right here shows the raw material margin in each period time of the year and its rate of return. So with our current design, the raw material margin is 7.9%, 7.95 cents per pound, and result a rate of return of 8.72%. And if you look at the year of 2013 and 2014, the price of the benzene and the propylene is quite high, and this result in a negative raw material margin, and it also result in an undeterminable rate of return due to the high value of the raw material cost compared to the cumene price. And if you look at the year of 2015 and 2017 to 2019, even though the price is reduced compared to the years of 2013 to 2014, but the raw material margin is still too tight and it falls in the range of 2.54 to 5.54, and it still result in an undeterminable rate of return. And only in the year of 2016 and 2020, the price of the benzene and the propylene is cheap enough, so the raw material margin is quite high, and it result in a rate of return above 15%, which is 36.4% in the year of 2016 and 28.1% this year. So from this analysis, it can conclude that a reduction in the benzene and propylene will be required for us to improve the rate of return of our projects. And a proposed solution, our proposed solution for this sensitivity study is that we can try to buy like benzene and propylene at cheap price this year due to the COVID-19 pandemic, and we stock it until we start to operate the plant in the 2023, and then hopefully we can produce and sell it at the cumene price provided by the purchasing department. So the second factor that also has a big impact on the rate of return of our project is a waste incineration cost. So here's a pie chart of the breakdown of our total utility cost, in which the waste cost contribute to 63% of the total utility cost. And from our data, we calculated that a reduction of more than 28.7% in the waste cost will help us to increase the rate of return above 15%. And our group also proposed solution for this sensitivity study is to increase the temperature of the benzene heavy column. So due to the temperature limitation at 470 degrees and the period specification of the IPP top stream column, so our benzene heavy column is not run really effectively, and the efficiency is quite low and fall in the range of 49% to 50%. And so by increasing the temperature, it will help us to increase the efficiency of the column, which will help to separate the IPP more effectively. So less weight will be coming out at the bottom and will be pushed out. And also, we don't have to spend any more money to upgrade the column to more stay or size it bigger to operate the column at a higher temperature. And ideally, with this solution, we also believe that all the DIPP can be removed from the heavy waste, and a 79% reduction of the amount of the heavy waste which will help us to save around $11.6 million per year for the operating cost. And in addition, if the column is run more effectively, more DIPP will be separated and recycled back into the transalkylation reactor. which will so less benzene will be required to fit into the process, which will also reduce raw material costs.
Along with the sensitivity analyses, an alternate process was studied which included the addition of a sixth column to the plant in order to assess its effect on the overall profitability. This column would be added after the initial benzene toluene column in order to purify a stream that was previously going to be used as fuel credit. The column was modeled in Aspen and sized to find a 4% increase to capital. With that increase in cost, we did find an increase in profitability. We saw an 8.5 increase to the ATROR from the initial base case design and a $26.6 million increase in net present worth over the plant's lifespan. And this was due to a $7.13 million increase in revenues from selling that purified benzene and toluene. In the end, it was determined that the current base case design would not lead to a profitable plant and thus should not be built as is under the current market conditions. As we saw, the present worth of the plant over its lifespan was found to be negative, and the rate of return was found to be only about 8.7%, which was much lower than the target 15%. We did see, however, that given changes in the market conditions, such as an increase to the price of cumene, the plant would become profitable. It would only require an increase in the price of cumene by about 0.66 cents per pound for the plant to reach a 15% rate of return and a positive present worth. Additionally, the sensitivity analyses and the alternate process study showed promise to alterations of the base case that would lead to a profitable plant. With promise of the possible profitability of an altered base case design, it is recommended that further analyses be conducted. First of all, we would recommend to explore the possibility of fluctuations in the current market prices of the byproducts and products coming from the system. Sensitivity analyses revealed that these do affect the economics and can have an effect on whether the plant is profitable or not profitable in the end. Secondly, we would recommend to explore possible design adjustments that could be made in order to lower the feed flow rates of the propylene and benzene streams entering the plant. These were our highest operating costs, so if we were able to lower those while still meeting capacity, it could help in making the base case profitable. Third, we would always recommend the research and development team to look into all assumptions that we made and to make sure that they are valid for the project. Fourth, something that is specific to the current global situation would be to consider the price of natural gas. Right now, it's at an all-time low, and whenever the plant is operating 3 years from now, the price might have increased back to around its normal price, which would increase our utility costs and then would have an effect on the possible profitability of the plant. So it's definitely something that would want to be considered moving forward. Lastly, one of our most promising leads is to look into the addition of the sixth column in order to purify the benzene and toluene to be sold. We would recommend that we continue with this alternate process study and to put the modeled Aspen of the single column into the Aspen file of the whole plant to check for its viability. And if it did run with everything, we would recommend to make this the new base case for the plant and move forward with that design.